we made a lot of progress since the first observation of the Higgs boson in 2012. This was already 10 years ago, especially concerning the interactions of the Higgs with other particles of the standard model, like quarks and bosons. There is, however, a lot of progress to make still, and many open questions. And in particular, now we are at a stage where we can start to test and to probe the interaction of multiple Higgs bosons together, so self-interactions. And this is important because it will provide us much more insight on the shape of the Higgs boson potential, which has a key role in the mechanism of spontaneous breaking of electroweak symmetry, which is needed to explain the mass of the standard model particle. So the most direct approach is to look for two Higgs bosons, which can decay into detectable particles in the ATLAS experiment. These processes are 1,000 times more rare than just producing a single Higgs boson. During the entirety of the LHC round 2 data taking, we only produced more or less 5,000 events with two Higgses. So to find these processes, we explore three different final states, with both Higgses which decay to bottom quarks, or one Higgs decaying to bottom and the other decaying to either photons or tau leptons. Then we have an alternative indirect approach to look for Higgs self-interactions, which consists in looking for events where there is only one Higgs boson produced. Some of these events will receive a very small correction due to the presence of two Higgses interacting together and resulting in a single Higgs boson in the final state. These effects are very, very tiny, at most 5%, but since we produce many events with one Higgs boson in the ATLAS detector, we can be sensitive to Higgs self-interactions through this type of studies. The most striking example of the results for direct searches of two Higgs bosons is this ATLAS plot. So here you can see the upper limits on the rate of production of two Higgs bosons in the ATLAS detector. This is really like searching for two needles in a very, very large haystack. And we are now able to exclude the production of two Higgs bosons down to 2.5 times the standard model expectation. So this means that if there were new physics phenomena that could enhance this process up to 2.5 times larger than what it is, we would have already seen them in ATLAS. We are also able to measure simultaneously the Higgs self-interaction magnitude, which is this kappa lambda parameter on the x-axis, together at the same time with the strength of Higgs interaction to the top quark, which is the k-top on the y-axis. This is really a key test, because if there was a new physics, this could really affect at the same time both Higgs self-interactions and the coupling of the Higgs to any other standard model particles. So the results that we find are well consistent with the standard model, which is the black star at the center of the plot, and we're able to exclude all of the values of the parameter which are outside the contour curves. So the results of all of these investigations really suggest that the way in which Higgs interact with itself, it's very close to what the standard model is predicting. But at the same time, we are at a stage where we cannot exclude new physics scenarios because we don't have enough data. We are really at the stage where the LHC is restarting, so we are all eagerly looking forward to the imminent restart, the round 3 data taking.